March 1943, Freeport, Texas. American aircraft production was about to collapse. Without magnesium, bombers couldn't fly, fighters couldn't climb, and the war in the sky would be lost. The nation's best engineers stared at production numbers that spelled disaster, extracting tiny amounts from stubborn rocks while the military demanded 10 times more. Then one desperate man looked out his office window at something he'd seen every single day for 3 years, but never really noticed. The Gulf of Mexico stretched to the horizon, billions of gallons holding the answer to America's crisis in dissolved form. But knowing the ocean held magnesium and actually extracting it were two completely different problems. The solution would require technology that didn't exist, expertise America didn't have, and the cooperation of men who had been shooting at Allied soldiers just months earlier. What happened next challenged everything people believed about loyalty, nationality, and what becomes possible when survival demands the impossible. Stay tuned. March 1943, Freeport, Texas. The Dow chemical plant stretched along the Gulf Coast like a sleeping giant, its smokestacks reaching toward a sky that had turned the color of old brass as the sun began its descent. Inside the main production facility, Chief Engineer Robert Hartley stood in front of a wall-sized production chart, his fingers trembling as he traced the declining numbers with a pencil that had been sharpened down to almost nothing. The numbers didn't lie, and they told a story that could change the outcome of the war. America was running out of magnesium, and without magnesium there would be no bombers, no fighter planes, no incendiary bombs to rain down on enemy positions. The aluminum alloys that formed the skeleton of every aircraft rolling off assembly lines from Seattle to Long Island required magnesium, and the current production methods were failing spectacularly. Hartley had been working 18-hour days for the past 3 months, watching as his teams extracted magnesium from dolomite rock, using processes that consumed enormous amounts of electricity and produced yields so low they made him want to throw his clipboard through the nearest window. The problem wasn't the workers or the equipment or even the raw materials, it was the fundamental chemistry, the stubborn way that magnesium locked itself into compounds that refused to give up their secrets easily. Outside, a supervisor named Mitchell was shouting at a group of workers who had just lost another batch to contamination, his voice carrying across the facility floor with the kind of desperation that comes from knowing your job might evaporate if the solution doesn't appear soon. The military liaison had visited 3 times that week alone, each visit more tense than the last, each conversation ending with thinly veiled threats about what happens to facilities that can't meet wartime quotas. Hartley walked out onto the observation deck and stared at the Gulf of Mexico, watching waves crash against the rocky shore with a rhythm that seemed to mock the chaos inside the plant. Somewhere out there in the Pacific, American pilots were flying missions in planes that might be the last ones produced if this problem wasn't solved. In Europe, bombing campaigns were being scaled back because the strategic planners knew they couldn't replace aircraft losses at the current rate. The ocean stretched out before him, vast and indifferent, its surface catching the last rays of sunlight and throwing them back in scattered diamonds of reflected light. He had been staring at that ocean for 3 years now, watching it every day from this same spot, and it had never once occurred to him that the solution might be floating right there in front of his face. The irony would haunt him later, but right now all he felt was the crushing weight of failure pressing down on his shoulders like a physical thing. Behind him the facility hummed and clanked and hissed, a symphony of industrial effort that was producing maybe 1/10 of what the nation needed to maintain air superiority in 2 theaters of war simultaneously. His assistant, a young chemist named Patterson, who had graduated from MIT just before Pearl Harbor, approached with another production report, and Hartley didn't even need to look at the numbers to know they were bad. Patterson had that look on his face, the one that said he'd rather be anywhere else delivering any other message to any other person. The report showed 3 more furnaces had failed overnight, their linings cracked from the extreme temperatures required to extract magnesium from mineral ore, and the replacement parts wouldn't arrive for another 2 weeks. In 2 weeks, the military planners had scheduled deliveries that would require triple the current output. The mathematics of the situation were brutally simple and completely impossible. Hartley took the report and walked back inside, past the furnaces that glowed like captured pieces of the sun, past the workers who looked at him with expressions that mixed hope and resignation in equal measure, past the quality control stations where technicians examined samples under bright lights and shook their heads more often than they nodded. The War Production Board had sent a telegram that morning, the words typed in all capitals like someone was shouting through the telegraph lines, demanding an explanation and a solution within 72 hours. 72 hours to solve a problem that had stumped the nation's best chemical engineers for the past year. 72 hours to figure out how to extract enough magnesium from stubborn rocks to keep the sky filled with American aircraft. He reached his office and closed the door, shutting out the noise of the facility, but not the weight of the problem, and that's when he noticed something he had never paid attention to before. On his desk sat a glass paperweight filled with seawater, a souvenir from his first day at the plant, a little piece of the Gulf captured in glass and placed there by his wife, who thought it might remind him why he had taken this job in the first place. The water inside had evaporated slightly over the years, leaving behind a thin crust of salt around the inside of the glass. Salt, minerals, dissolved solid. The ocean was essentially a giant solution of dissolved minerals, including magnesium, and he had been staring at the largest source of magnesium on the planet every single day without seeing it. The archive discovery sparked renewed interest in the story, leading to articles and eventually a documentary film that interviewed surviving participants and examined the unusual collaboration that had solved America's magnesium crisis. Patterson, in his 90s and still sharp despite his age, gave extensive interviews describing Zimmermann's contributions and the atmosphere of cooperation that had developed despite the circumstances. He emphasized that the success had come not from any single innovation, but from the combination of theoretical knowledge and practical experience and willingness to set aside preconceptions about who could be trusted and what was possible. The German engineers had brought expertise developed in different industrial contexts and applied it to American problems, while American engineers had provided resources and infrastructure that made implementation possible at scales the Germans couldn't have achieved alone. The collaboration had worked because both groups recognized that technical challenges transcended nationality and that solving those challenges required the best available knowledge, regardless of its source. The story resonated with contemporary audiences facing their own questions about international cooperation and immigration, and the movement of technical knowledge across borders. Some commentators drew parallels to modern scientific collaborations that bring together researchers from different nations to address global challenges, while others focused on the irony of enemy combatants contributing to the war effort against their own country. The ethical complications remained unresolved even decades later, with legitimate questions about whether the prisoners had been truly voluntary participants, or whether their captivity had coerced cooperation regardless of individual preferences. Zimmermann's letters and interviews suggested that he had viewed his work as consistent with his opposition to Nazi ideology, that helping defeat Germany meant helping to liberate it from totalitarianism, but not all the German engineers had shared that perspective, and some had cooperated primarily to improve their conditions rather than from ideological commitment. The facility continued operating into the 21st century, upgraded and modernized but still following the basic process developed during those desperate months in 19. Modern sensors and computer controls had replaced analog gauges and manual adjustments. Automated systems managed processes that had once required constant human attention, and environmental protections ensured that operations didn't damage coastal ecosystems. But the fundamental chemistry remained unchanged: seawater treated with lime to precipitate magnesium hydroxide, converted to chloride and electrolyzed to produce pure metal. The ocean that Hartley had stared at from his office window continued providing raw material for processes he had helped develop, a renewable resource that required no mining or excavation, just the patient extraction of dissolved minerals from water that would return to the Gulf essentially unchanged. The technology had spread globally, with major facilities operating in China and Russia and Israel and Norway, producing magnesium for markets that Hartley and Zimmermann couldn't have imagined during wartime. The metal went into smartphones and laptops and electric vehicle components, applications far removed from the aircraft structures that had necessitated its wartime development. The story of how that technology emerged, how desperate necessity had forced innovation, and how unlikely collaborations had produced breakthrough solutions, provided lessons about the nature of technical progress and the importance of drawing on diverse knowledge sources. It challenged simple narratives about wartime production that emphasized American ingenuity and self-reliance, revealing instead a more complex reality where success came from combining German chemistry with American industrial capacity and where former enemies worked together toward goals that transcended immediate circumstances. The archive also contained photographs from the facility during its wartime operations, images showing German prisoners in faded uniforms working alongside American engineers in hard hats. Both groups focused on equipment and processes rather than camera. The photographs captured moments of consultation and collaboration, Germans and Americans examining technical drawings together or adjusting equipment or monitoring production runs, scenes that looked like ordinary industrial work except for the context that made them extraordinary. There were also letters between Zimmermann and Hartley, from the years after repatriation, correspondence that documented their continuing friendship and professional collaboration and their shared perspective that the wartime project had been among the most meaningful work of their career. Both men expressed satisfaction that they had contributed to ending the war and to developing technology that would have value beyond immediate military application, and both acknowledged that circumstances they hadn't chosen had pushed them together in ways that enriched their lives despite the tragedy that had made their meeting possible. The final materials in the archive included Zimmermann's speech at the facility's 40th anniversary celebration in 1983, one of the few times he spoke publicly about his wartime experience. He described the initial skepticism and hostility he had encountered, the gradual development of professional respect, and his gratitude for the opportunity to use his skills against the regime he opposed. He emphasized that technical knowledge belonged to humanity rather than to specific nations and that the greatest achievements came from pooling expertise rather than hoarding it. He also noted the irony that his most significant contribution to chemistry had come while he was technically an enemy of the United States, and he expressed hope that future generations would find ways to collaborate across borders without requiring warfare to force cooperation. The speech received a standing ovation from an audience that included many of the American engineers who had worked with him during those intense months in night, and photographs from the event showed elderly men in suits greeting each other with the warmth of people who had shared extraordinary experiences. The facility they had built together continued humming in the background, processing seawater and producing magnesium through processes they had pioneered, a permanent testament to what could be achieved when technical excellence took precedence over political divisions, and when people found common purpose despite belonging to different sides of history's bloodiest conflict. The ocean that had provided the solution to America's wartime crisis continued its ancient patterns, waves carrying minerals that would be extracted and processed and transformed into materials that shaped the modern world, a cycle that had begun in desperation and continued through decades of peacetime prosperity, connecting past urgency to present utility through chemistry that transcended the circumstances of its discovery. Hartley stood frozen in his office, the paperweight clutched in his hand like a religious artifact that had suddenly revealed its true purpose. The seawater inside caught the light from his desk lamp and threw tiny caustics across the ceiling, dancing patterns that seemed to pulse with possibility. He set the paperweight down carefully, as if it might shatter and take his revelation with it, and reached for the telephone on his desk. Patterson answered on the first ring, probably sitting at his station waiting for more bad news, and Hartley could hear the resignation in his voice before he even finished saying hello. But Hartley wasn't calling with bad news this time. He told Patterson to get to his office immediately and to bring every chemistry reference book he could carry, especially anything related to seawater composition and mineral extraction. Patterson showed up 7 minutes later, his arms loaded with textbooks that dated back to before the Depression, their spines cracked and pages yellowed, but their information still valid, still true, still potentially revolutionary. They spread the books across Hartley's desk and began cross-referencing compositions, concentrations, extraction methods, and industrial processes. The numbers that emerged from their research were staggering. Ocean water contained approximately 1,300 parts per million of magnesium, which sounded like nothing until you considered the sheer volume of the ocean itself. Every cubic kilometer of seawater held about 1.3 million kilograms of dissolved magnesium, just floating there, waiting for someone to figure out how to extract it efficiently. The Gulf of Mexico alone represented a virtually infinite source of the metal they so desperately needed, renewable and inexhaustible, limited only by their ability to process it. Patterson looked up from his calculations with an expression that mixed excitement and disbelief in equal measure, his pencil scratching notes faster than Hartley had ever seen him write. They spent the next 6 hours working through theoretical extraction processes, building on research that dated back decades to chemists who had studied seawater composition as an academic exercise, never imagining their work might become critical to national survival. The basic process seemed almost absurdly simple in concept, though the execution would require solving a dozen engineering challenges simultaneously. They would treat seawater with lime to precipitate out the magnesium as magnesium hydroxide, then convert that hydroxide to magnesium chloride using hydrochloric acid, and finally electrolyze the chloride to produce pure metallic magnesium. Each step had been demonstrated in laboratory settings before, but nobody had ever attempted to scale the process to industrial production levels. By midnight they had sketched out a preliminary design for a pilot plant that could process thousands of gallons of seawater per hour, and Hartley felt something he hadn't experienced in months, the electric tingle of genuine hope. He called an emergency meeting of the senior engineering staff for 6 in the morning, knowing that half of them would show up thinking they were about to be fired or reassigned, or told that the facility was being shut down entirely. Instead, he presented them with drawings and calculations and projections that showed how they could potentially increase magnesium production by a factor of 10 within 6 months, maybe more if they could solve the engineering challenges fast enough. The room fell silent when he finished his presentation, the kind of silence that precedes either revolutionary acceptance or complete rejection, and Hartley held his breath while his colleagues processed what he had just told them. Johnson, the senior metallurgist who had been with Dow since before the last war, was the first to speak, and his words came out in a mixture of skepticism and desperate hope. He pointed out that the ocean wouldn't stay still while they pumped millions of gallons through processing plants, that storms would shut them down, that salt would corrode their equipment faster than they could replace it, that the chemistry looked good on paper but might fall apart in practice. Every objection was valid, every concern was real, and Hartley acknowledged each one, while emphasizing that they didn't have the luxury of perfection. They needed solutions and they needed them immediately. Mitchell, the production supervisor who had been shouting at workers just hours earlier, raised the question of manpower, noting that their current workforce was already stretched beyond breaking and that building an entirely new processing system would require hundreds of additional workers at a time when every able-bodied man was either in uniform or working in another essential industry. The labor shortage was crushing every war production facility in the nation, and there was no magical pool of skilled workers waiting to be hired. That's when Hartley mentioned something he had heard through unofficial channels, rumors that had been circulating through the industrial complex about a potential solution to the manpower crisis that nobody wanted to discuss openly, because it seemed too controversial, too risky, too unprecedented to actually implement. There were German prisoners of war arriving in camps throughout the Southwest, thousands of them, captured in North Africa, and shipped across the Atlantic to facilities that were already struggling to house and feed them. The Geneva Convention required that prisoners be treated humanely and could be employed in non-combat work, and someone in Washington had apparently decided that non-combat work might include industrial production for the war effort. The room fell silent again, but this time the silence carried a different weight, the uncomfortable tension of people confronting an idea that challenged their assumptions about who could be trusted and what was possible in wartime. Camp Swift sat in the scrubland outside Austin, Texas, a sprawling collection of wooden barracks and guard towers that had been thrown together in less than 3 months to house the sudden influx of prisoners that began arriving after Rommel's Africa Corps collapsed in Tunisia. Captain James Wheeler commanded the facility, a position he had neither requested nor particularly wanted, but the army had a way of putting people where they were needed regardless of personal preference. He stood in his office looking at requisition forms and status reports, and incident logs that documented the daily reality of keeping several thousand enemy soldiers confined and occupied in the middle of nowhere. The prisoners were mostly young men, some barely out of their teens, wearing uniforms that had faded from their original field gray to a dusty tan that matched the Texas landscape. They moved through their daily routines with the mechanical efficiency of people who had adapted to captivity, accepting their meals and assignments and confinement with an attitude that mixed resignation and relief. Most of them seemed glad to be out of the war, glad to be alive, glad to be somewhere that wasn't a battlefield or a transport ship or a temporary holding facility in North Africa. Wheeler had discovered that many of them were skilled workers in civilian life, trained as machinists or electricians or chemical technicians before the Nazi war machine had conscripted them and sent them marching across deserts and mountains. That expertise was currently being wasted on basic camp maintenance and agricultural work, tasks that kept them busy but didn't utilize their actual capabilities. When the telegram arrived from the War Production Board, Wheeler read it 3 times before fully processing what Washington was asking him to do. They wanted to know if he had prisoners with industrial chemistry experience, specifically anyone who had worked in mining or metallurgy or chemical processing facilities. The telegram included security clearance requirements and background check procedures and a series of questions about loyalty and cooperation levels that seemed designed to identify prisoners who might be trusted with work outside the camp perimeter. Wheeler called in his chief interrogator, a lieutenant named Braun who spoke fluent German and had been conducting detailed interviews with prisoners since the camp opened. Braun kept meticulous files on every prisoner, documenting their military service, their civilian backgrounds, their political affiliations, and their attitudes toward the Nazi regime. Over months of careful conversation, Braun had identified several men who seemed genuinely disillusioned with Hitler and everything the Third Reich represented. Soldiers who had fought because they had no choice but who harbored no particular loyalty to the ideology that had sent them to war. Among those files was a dossier on a prisoner named Klaus Zimmermann, a chemical engineer from Leipzig, who had worked at IG Farben's Luna plant before being drafted into the Wehrmacht. Zimmermann's file noted that he had been overheard expressing disgust at Nazi policies, that he had never joined the party despite pressure to do so, and that he possessed extensive knowledge of industrial chemical processes, including the extraction of minerals from complex solutions. Braun also flagged a machinist named Otto Schultz, a metallurgist named Franz Weber, and an electrical engineer named Heinrich Kohler, all of whom had similar backgrounds and similar attitudes. These men represented exactly the kind of skilled labor that could make the Seawater magnesium extraction project feasible, but they were also enemy combatants being asked to contribute directly to the American war effort. Wheeler arranged a meeting with Zimmermann first, bringing him to a small interview room where the only decoration was a map of the United States with pins marking various military installations. Zimmermann sat across from Wheeler, with an expression of cautious curiosity, probably wondering if he was about to be accused of something or transferred somewhere worse. Instead, Wheeler explained the situation in careful terms, outlining the magnesium crisis and the proposed seawater extraction process, and the need for engineers who understood industrial chemistry at a practical level. He emphasized that any work would be voluntary, that cooperation would be noted in their prisoner records, and that conditions would be significantly better than sitting in camp barracks watching dust blow across empty fields. Zimmermann listened without interrupting, his face betraying nothing except intense concentration, and when Wheeler finished speaking, the silence stretched out for almost a minute before the German engineer responded. His English was accented but clear, each word chosen carefully, and what he said changed everything. He explained that he had actually worked on a similar project at Luna in the late 30s, attempting to extract magnesium from potash mining waste, and while that project had ultimately been abandoned for economic reasons, the basic chemistry was similar to what Wheeler was describing. He understood the process, knew the potential pitfalls, and could probably contribute meaningfully to solving the engineering challenges, but he wanted something in return, something beyond better conditions or favorable mention in his prisoner file. He wanted Wheeler to understand that helping America win the war meant helping to defeat Germany, and that helping to defeat Germany meant helping to destroy the Nazi regime, and that for him, that was not a conflict of loyalty, but rather a moral obligation. He had seen what Hitler's government had become, had watched as colleagues disappeared for asking wrong questions or expressing wrong opinions, had witnessed the transformation of his country into something unrecognizable and terrible. If working in an American chemical plant could contribute even slightly to ending that nightmare, then he would consider it an honor rather than a betrayal. The pilot plant rose from the coastal landscape like something that had grown there, organically rather than being built by human hands, a tangle of pipes and tanks and scaffolding that followed the natural contours of the shoreline while maintaining the geometric precision required for industrial chemistry. Hartley had selected a site 3 miles from the main Dow facility, close enough for support infrastructure, but far enough that any catastrophic failures wouldn't cascade into the primary production areas. The construction had begun in late April, barely 6 weeks after the revelation in his office, and now in early June the skeleton of the operation was taking shape under the relentless Texas sun. The workforce was unlike anything Hartley had ever supervised, a mixture of American construction workers, Dow chemical engineers, and German prisoners of war, who moved through the site wearing identifying armbands and working under the constant supervision of military police. Zimmermann had arrived with 14 other German engineers and technicians, all of whom had been carefully screened and all of whom had agreed to work on the project for reasons ranging from pragmatic self-interest to genuine ideological opposition to the Nazi regime. The American workers had been skeptical at first, uncomfortable working alongside men who had recently been shooting at Allied soldiers, but practical necessity and professional respect had gradually broken down most of the initial barriers. Zimmermann proved to be exactly the asset Hartley had hoped for, identifying potential problems before they developed and suggesting modifications to the process flow that saved weeks of trial and error refinement. The German engineer would stand in front of technical drawings with Patterson and the other American chemists, explaining in careful English how they had handled similar challenges at Luna, what had worked and what had failed, and why certain approaches would prove problematic at scale. His insights were so valuable that Hartley began including him in design meetings alongside senior Dow personnel, a decision that required special authorization from both military intelligence and corporate headquarters, but which paid immediate dividends in accelerated development. The basic system they designed consisted of massive intake pipes that would draw seawater directly from the Gulf, preliminary filtration tanks to remove sand and organic material, reaction vessels where lime would be added to precipitate magnesium hydroxide, settling tanks where the precipitate could be separated from the treated water, and finally the conversion and electrolysis stages that would produce pure metallic magnesium. Each stage required precise control of temperatures, concentrations, and flow rates, and the entire system needed to operate continuously to be economically viable. Schultz, the German machine, had taken charge of fabricating specialized pumps that could handle the corrosive properties of seawater without failing. After a few days of operation, while Weber focused on the metallurgy of the electrolysis cells and Kohler worked on the electrical systems that would power the entire facility. By mid-June they were ready for the first test run, a moment that would either validate months of theoretical work or reveal fundamental flaws in their approach. Hartley gathered the entire team at dawn, knowing that whatever happened in the next few hours would determine whether the project continued or was abandoned as an expensive failure. They opened the intake valves and watched as seawater began flowing into the system, filling the preliminary tanks with ocean water that looked deceptively innocent considering what they were about to do to it. The first stage involved adding lime slurry to the filtered seawater, a process that should precipitate out the dissolved magnesium as magnesium hydroxide while leaving most other minerals in solution. Zimmermann stood at the reaction vessel with a stopwatch and a clipboard, monitoring temperatures and pH levels and reaction rates with an intensity that made everyone around him nervous. After 20 minutes he nodded to Hartley and gestured toward the settling tank, where a white precipitate was beginning to accumulate at the bottom, visible through inspection ports as a cloudy layer that grew thicker as they watched. The chemistry was working, the magnesium was coming out of solution, and the first major hurdle had been cleared. They transferred the precipitate to the conversion stage, where it would be treated with hydrochloric acid to produce magnesium chloride, the form required for electrolysis. This stage was more complicated because the acid had to be carefully controlled to avoid producing unwanted byproducts that would contaminate the final metal. Weber monitored the process with instruments borrowed from the main Dow facility, making constant adjustments to maintain optimal conditions, and after 2 hours they had produced a batch of magnesium chloride that met the purity specifications required for electrolysis. The final stage involved passing electrical current through the molten chloride to separate the magnesium from the chlorine, a process that consumed enormous amounts of electricity and generated intense heat. They had built a small electrolysis cell for the pilot plant, nothing like the industrial-scale cells that would eventually be required, but sufficient to demonstrate that the entire process could work from start to finish. Kohler threw the switch that activated the electrical systems, and everyone held their breath as current began flowing through the molten salt. The cell hummed with power, glowing with internal heat that radiated across the observation area, and after 15 minutes of nail-biting tension, a small bead of silvery metal began forming at the cathode, growing larger as the electrolysis continued, until Zimmermann carefully extracted a sample that weighed maybe 50 grams but represented the proof that they had successfully extracted magnesium from seawater. The success of the pilot plant triggered a bureaucratic avalanche that threatened to bury the project under mountains of paperwork and authorization requests, and security clearances that nobody had anticipated being necessary when they started. Hartley spent 3 weeks shuttling between Freeport and Washington, presenting results to committees and boards and officials who wanted to be convinced that scaling up the operation wouldn't result in catastrophic failure or security breaches or diplomatic incidents. The German prisoners working on the project had become a particular point of contention, with some officials arguing that they should be removed immediately, while others insisted that their expertise was too valuable to waste on ideological concerns. Hartley defended Zimmermann and the other Germans with a ferocity that surprised even himself, pointing out that they had solved problems in weeks that might have taken American engineers months to figure out, and that removing them now would effectively guarantee delays that the nation couldn't afford. Eventually, after countless meetings and presentations and demonstrations, the authorization came through to proceed with full-scale construction of a facility that would dwarf the pilot plant by several orders of magnitude. The budget approval was staggering, more money than Hartley had ever been responsible for in his entire career, and the timeline was aggressive to the point of absurdity, requiring them to go from concept to full production in less than 8 months. They broke ground on the main facility in late July, choosing a site that had direct access to deep water and existing electrical infrastructure and rail connections for shipping finished magnesium to aircraft manufacturers. The construction crew grew to over 3,000 workers operating around the clock in shifts that blurred together into a continuous assault on the landscape. Engineers from Dow brought in equipment and expertise from other facilities, while military engineers contributed knowledge gained from building airfields and supply depots under combat conditions. Zimmermann had been promoted from consultant to deputy chief engineer, a position that required special dispensation from military intelligence and which made him technically senior to several American engineers, who struggled with the idea of taking direction from a prisoner of war. But Zimmermann had earned his position through demonstrated competence rather than political maneuvering, and most of the American staff recognized that his contributions were essential to meeting the impossible deadline. The German engineer worked longer hours than anyone else on the project, often sleeping in a converted office near the construction site rather than returning to the camp each night, and his dedication gradually won over even the most skeptical members of the team. The main facility incorporated everything they had learned from the pilot plant while scaling up the capacity by a factor of 50. They built intake structures that could draw 10 million gallons of seawater per day from the Gulf. Massive reaction vessels where hundreds of tons of lime would be mixed with filtered seawater, settling tanks the size of swimming pools where magnesium hydroxide would accumulate before being pumped to conversion units, and an entire building dedicated to electrolysis cells arranged in rows that stretched the length of a football field. Each cell represented a miniature version of the process they had perfected in the pilot plant, but managing hundreds of them simultaneously introduced complexity that pushed the limits of existing control technology. Patterson had been assigned to develop the monitoring systems that would track temperatures and currents and chemical concentrations across the entire facility, using analog gauges and manual recording systems, because digital process control wouldn't be invented for another decade. The electrical requirements alone were staggering, requiring them to build a dedicated substation connected directly to the regional power grid, and the utility company had expressed serious concerns about whether their infrastructure could handle the sustained load. Kohler worked with electrical engineers from Dow and the power company to design a distribution system that could deliver the necessary power without overloading existing transmission lines, a challenge that required creative solutions and custom-built transformers that had to be manufactured specifically for the project. By September, the main structures were complete and they began installing process equipment, a phase that revealed new problems almost daily. Pumps that had worked flawlessly in the pilot plant failed after hours of operation at full scale, gaskets dissolved under chemical attack that hadn't been anticipated during design, and flow rates that looked good on paper created turbulence that interfered with precipitation in ways they didn't fully understand. Zimmermann and his German colleagues worked alongside American engineers to solve each problem as it emerged, often improvising solutions on the spot using whatever materials and equipment were available. The collaboration had evolved from grudging necessity to genuine professional partnership, with nationality mattering less than competence and creativity in the face of urgent challenges. Weber discovered that adding small amounts of aluminum to the electrolysis cell design dramatically improved metal purity and reduced power consumption, a modification that would save millions of dollars over the facility's lifetime. Schultz redesigned the pump impellers to handle the abrasive nature of precipitate-laden slurry, using techniques he had learned in German mining operations, and adapting them to the specific conditions they faced on the Texas coast. The facility began partial operations in late October, processing seawater through the first stage of the operation, and producing magnesium hydroxide in quantities that dwarfed anything achieved during the pilot plant. December 1943 brought the first real test of the facility's capabilities, when the War Production Board issued an emergency order for 30 tons of magnesium to be delivered within 2 weeks, quantities that would have been impossible under the old extraction methods, but which represented barely 10% of the new facility's theoretical capacity. Hartley read the order with a mixture of excitement and terror, knowing that success would validate everything they had built, while failure would raise questions about whether the entire project had been worth the massive investment. They brought all systems online simultaneously for the first time, opening intake valves that began drawing seawater from the Gulf at rates that created visible currents in the coastal waters. The facility came alive with sound and motion and energy, pumps throbbing with mechanical heartbeats, reactors hissing as chemicals mixed and transformed, electrolysis cells humming with electrical power that flowed through them in rivers of charged particles. Zimmermann had established himself in the main control room, a space that resembled a ship's bridge more than a traditional factory office, with gauges and indicators and status boards that showed the condition of every major system in real time. Patterson coordinated with shift supervisors to maintain optimal operating parameters across all stages of the process, making constant adjustments as they learned how the scaled-up facility behaved under full load. The first challenges emerged within hours as pumps that had never operated at design capacity began showing signs of strain, bearings overheating and seals weeping fluid in ways that threatened to escalate into major failures. Schultz deployed maintenance teams to address problems as they developed, often fabricating replacement parts on site using machine shops that had been set up specifically for emergency repairs. The reaction vessels performed better than expected, precipitating magnesium hydroxide with efficiency that exceeded their design calculations, but the settling tanks revealed a problem nobody had anticipated. The precipitate was settling more slowly than predicted, probably due to particle size distributions that differed from the pilot plant, and the slower settling meant reduced throughput unless they could modify the process. Weber proposed adding flocculants to accelerate particle aggregation, chemicals that would make the fine particles clump together into larger masses that would settle faster under gravity. The modification worked brilliantly, reducing settling time by almost half and allowing them to maintain target production rates despite the unexpected behavior. By the end of the first week they had established a rhythm, each shift learning from the previous one, and passing along insights and adjustments that gradually optimized the entire operation. The electrolysis cells proved to be the most demanding aspect of the facility, requiring constant attention to maintain proper temperatures and current densities and electrolyte composition. Kohler had trained a team of German and American technicians to monitor the cells around the clock, responding to variations before they could cascade into problems. Each cell produced maybe 10 kilograms of magnesium per day, but with over 200 cells operating simultaneously, the facility was generating more than 2 tons of pure metal every 24 hours. They had built specially designed molds to collect the molten magnesium as it formed at the cathodes, allowing it to solidify into ingots that could be easily handled and shipped. The first ingots emerged on the 5th day of full operation, gleaming bars of silvery metal that represented the culmination of months of engineering effort and the cooperation of people who had started as enemies, but had become colleagues working toward a common goal. Hartley held one of those ingots in his hands, feeling its surprising lightness and running his fingers across its surface, and allowed himself a moment of satisfaction before returning to the immediate demands of maintaining production. The facility reached its target of 30 tons with 2 days to spare, shipping the magnesium to aluminum smelters and aircraft manufacturers, who had been desperately waiting for supply. The success triggered a cascade of new orders from military planners, who suddenly realized they had access to essentially unlimited quantities of magnesium as long as the facility kept operating. Hartley and his team began planning expansions even before the first production run was complete, designing additional electrolysis buildings and reaction vessels and intake structures that would triple capacity within 6 months. Zimmermann had become indispensable to the operation, his knowledge of industrial chemistry and his ability to troubleshoot complex systems making him the person everyone turned to when problems emerged. The German engineer had also become something of a bridge between the American staff and the other German prisoners working at the facility, translating not just language but also culture and approach, helping both groups understand each other's methods and perspective. The arrangement had settled into an unusual equilibrium where nationality mattered less than competence and where former enemies worked side by side toward goals that transcended the immediate circumstances of the war. Not everyone was comfortable with the situation, and there were still tensions and resentments that occasionally surfaced, but the demands of maintaining production left little time for ideological dispute. By January 1944, the facility was producing over 60 tons of magnesium per month and operating with reliability that exceeded anything Hartley had dared to hope for during those desperate days back in March when the numbers on his production chart had spelled potential disaster. The social dynamics around the magnesium facility had evolved in ways that nobody could have predicted when the project began, creating a microcosm where the boundaries between captor and prisoner, ally and enemy, became blurred by the practical demands of industrial production. Zimmermann and Hartley had developed something resembling friendship, though neither would have used that word exactly, a relationship built on mutual respect and shared purpose that transcended the circumstances that had brought them together. They would spend evenings reviewing production data and planning maintenance schedules and discussing modifications to improve efficiency. Conversations that gradually expanded to include personal histories and observations about the war and speculations about what would happen when the conflict eventually ended. Zimmermann spoke carefully about his life before the war, describing his work at Luna and his education at Leipzig and his growing disillusionment as the Nazi regime tightened its grip on German society. He had watched colleagues arrested for political unreliability, seen books burned and professors dismissed and research redacted toward military applications, and he had felt increasingly trapped in a system he fundamentally opposed but lacked the power to resist. His service in North Africa had been a strange relief, combat duty that was at least honest in its brutality, rather than the suffocating conformity of civilian life under totalitarian control. Hartley shared his own background, explaining how he had come to chemical engineering through a circuitous route that included failed attempts at medical school and a brief career as a high school chemistry teacher, before discovering that industrial applications were his real calling. The conversations revealed commonalities that the war had obscured. Two men from different cultures who shared similar values and who had ended up on opposite sides of a conflict neither had wanted. The other German prisoners had formed their own relationships with American workers, bonds that developed slowly through shared problems and collaborative solutions, and the simple proximity of people working toward common goals. Schultz had become drinking buddies with an American machinist named Rodriguez, the two of them spending off hours swapping stories about mechanical disasters and clever repairs and the universal frustrations of working with equipment that never quite performed as designed. Weber had struck up an unlikely friendship with Patterson, the young MIT chemist, bonding over their shared fascination with material science and their mutual frustration with administrators who didn't understand technical details. These relationships weren't universal. Some American workers remained deeply hostile to the Germans, and some prisoners remained resentful of their captivity, but enough connections had formed to create an atmosphere that felt less like a guarded industrial facility and more like a specialized technical community brought together by unusual circumstances. The military police who supervised the German workers had gradually relaxed their vigilance as it became clear that nobody was planning escape attempts or sabotage, and their presence became more supervisory than overtly threatening. Captain Wheeler visited the facility monthly to review security arrangements and conduct interviews with prisoners to ensure they weren't being coerced or mistreated, and his reports consistently noted the unusual but functional nature of the operation. The arrangement had attracted attention from other military officials and industrial planners who were dealing with their own labor shortages, and who wondered if similar collaborations might be possible in other industries. There were visits from War Department observers and journalists who had been cleared to write about the facility, without revealing specific locations or technical details, and the resulting articles presented the operation as an example of pragmatic cooperation in service of victory. Not everyone approved of the arrangement. There were letters to editors and questions raised in Congress about whether employing enemy prisoners in war production was appropriate or whether it set dangerous precedent. But the sheer success of the facility made it difficult to argue for shutting it down or significantly changing its operation. By spring of 1944, the magnesium crisis had effectively been solved, with production from the Freeport facility and several new plants being built elsewhere providing more than enough material to meet aircraft production demands. The success had come from an unlikely combination of ocean chemistry and German engineering expertise, and American industrial capacity, a convergence that nobody could have predicted when Hartley first stared at that paperweight on his desk. The relationships formed during the project would last in some cases long after the war ended, with Zimmermann and several other German engineers eventually returning to work for Dow after being repatriated and then immigrating back to the United States as civilian employees. The facility itself would continue operating for decades, eventually transitioning from war production to commercial applications, and becoming one of the world's largest sources of magnesium for industrial use. But in that spring, what mattered most was that American bombers were flying and fighters were engaging, and the sky remained filled with aircraft that carried the aluminum-magnesium alloys extracted from seawater by people who had set aside national allegiances in favor of technical excellence and shared purpose. June 1944 brought news that changed everything for everyone working at the facility. Word of massive Allied landings in Normandy that signaled the beginning of the end for Nazi Germany. The American workers celebrated openly, while the German prisoners received the news with expressions that mixed inevitability and relief, and apprehension about what would happen to their homeland. Zimmermann stood on the observation deck where Hartley had experienced his revelation more than a year earlier, watching the Gulf waters reflect the colors of sunset and processing the reality that his country was facing defeat. Hartley joined him there without speaking, both men understanding that words were inadequate for moments like this, and they stood in companionable silence watching the waves and listening to the sounds of the facility operating below them. The invasion meant that American air superiority over Europe was total, that the bombers were flying without serious opposition, that the aluminum-magnesium alloys they had helped produce were carrying the war to Germany itself. Zimmermann knew that some of those bombs would fall on Leipzig, on the city where he had studied and worked and built a life before the Nazis destroyed everything, and he couldn't quite identify what he felt about that prospect. Part of him wanted to see the regime crushed regardless of the cost, while another part mourned for the innocent people who would suffer in the process. Hartley asked him what he would do after the war, whether he planned to return to Germany, or whether he might consider staying in America, and Zimmermann admitted he didn't know. The question opened up futures that had seemed impossible during the dark days of 1943, when survival had been the only concern worth contemplating. They talked about the possibility of continuing their collaboration, about applying the seawater extraction technology to other metals and minerals, about building an enterprise based on the lessons learned during wartime necessity. The conversation was speculative and cautious, neither man wanting to make commitments that circumstances might render impossible, but it represented a shift from viewing their relationship as temporary wartime cooperation to imagining something that might extend beyond the immediate crisis. Production at the facility had reached almost 200 tons per month by summer, a figure that seemed almost absurd compared to the desperate shortage that had prompted the project. The magnesium flowed out to aircraft manufacturers and found its way into bombers and fighters, and transport planes that were rewriting the strategic balance of the war. The success had sparked construction of 4 additional seawater extraction facilities along the Gulf Coast and 2 on the Pacific Coast, creating an entire industry that would outlive the conflict that had necessitated its development. The technology would eventually spread to other nations, with variations of the process being adopted in countries around the world wherever coastlines and industrial infrastructure intersected. But the human story of how that technology had been developed remained largely hidden. classified for security reasons and then simply forgotten as the world moved on to other concerns. The German engineers who had contributed so significantly to the project rarely spoke about their wartime service, some because they felt conflicted about having aided the Allied cause while their countrymen were dying, others because they had been sworn to secrecy about technical details that remained sensitive even after hostilities ended. Zimmermann would later describe the period as the most meaningful work of his career, a time when he had been able to use his skills to actively oppose the regime he despised while building something that would have value beyond the immediate circumstance. By autumn it was clear that Germany couldn't sustain the war much longer, that the combination of Eastern and Western pressure was crushing the Wehrmacht between forces it couldn't hope to defeat. The prisoners at Camp Swift received the news with varying degrees of emotion, some relieved that the slaughter would end, others devastated that their country was being destroyed, all of them uncertain about what would happen to them when victory finally came. Zimmermann had been assured by Hartley and Wheeler that his contributions would be documented and that he would be treated favorably in whatever repatriation and reconstruction process emerged, but promises made during wartime often evaporated when peace arrived and different priorities dominated. The facility continued operating through the winter of 1944 into 1945, maintaining production levels that had become routine rather than remarkable, the initial excitement of solving an impossible problem giving way to the steady rhythm of industrial operation. New workers replaced those who left for other assignments, and the presence of German prisoners became just another aspect of the operation, rather than something controversial or unusual. The war in Europe ended in May 1945 with Germany's unconditional surrender, and the prisoners at Camp Swift and other facilities throughout the United States faced an uncertain future as the victorious Allies determined what to do with millions of former enemy combatants. Zimmermann and the other German engineers working at the Magnesium facility were kept on through the summer as the military worked through repatriation logistics, and during those months they completed the training of American replacements who would maintain operations after the prisoners were sent home. Hartley had lobbied quietly but persistently for Zimmermann to be allowed to return to the United States after repatriation, arguing that his skills were too valuable to lose, and that he had demonstrated loyalty to democratic principles even when doing so meant opposing his own government. The paperwork moved slowly through bureaucratic channels, but eventually the authorization came through for Zimmermann and several others to immigrate as civilian technical experts once they had completed the required repatriation period in Germany. Zimmermann returned to Germany in autumn of 1945, and found a country that barely resembled what he had left 3 years earlier, cities reduced to rubble and infrastructure shattered, and society struggling to reconstitute itself from the ruins of totalitarian collapse. Leipzig had been bombed repeatedly during the final months of the war, and the neighborhood where he had lived before conscription no longer existed except as cleared lots and partial walls marking where buildings had once stood. He spent 6 months working in reconstruction efforts, using his engineering knowledge to help restore basic services to communities that lacked electricity, or clean water, or functional sewage systems. The work was necessary and important, but ultimately limited by the scale of destruction and the shortage of resources that made even simple repairs difficult to implement. When the authorization came through for him to return to the United States as a civilian immigrant, he accepted without hesitation, recognizing that Germany would take decades to recover and that his skills could be better utilized elsewhere. Hartley met him at the dock in Galveston in spring of 1946, and the two men shook hands with the formality of people who had worked together under extraordinary circumstances and were now attempting to rebuild that relationship under more normal conditions. Dow Chemical had offered Zimmermann a position as senior chemical engineer with a focus on expanding the seawater extraction operations and developing new applications for the technology. He accepted and began working at the Freeport facility again, this time as an employee rather than a prisoner, earning a salary that allowed him to rent an apartment and eventually purchase a house and start building the kind of stable life that had seemed impossible during the chaos of war. Several other German engineers from the wartime project followed similar paths, immigrating to the United States and finding employment in industries that valued their technical expertise, regardless of their nationality. The Magnesium facility had become a permanent fixture of the Gulf Coast industrial landscape, operating continuously and expanding periodically as demand grew. The technology developed during those desperate months in 1943 had evolved and improved, with better materials and more efficient processes, and automated controls replacing the manual systems that had characterized the original installation. But the fundamental approach remained the same, treating seawater with lime and extracting magnesium in a process that turned ocean water into metal with remarkable efficiency. The facility would eventually become one of many scattered along coastlines around the world, producing hundreds of thousands of tons of magnesium annually for applications ranging from aircraft construction to automotive manufacturing to pharmaceutical production. The wartime origins of the technology were gradually forgotten as younger generations of engineers learned the processes without understanding the context that had made their development necessary. Zimmermann continued working at Dow until his retirement in 1978, eventually becoming chief engineer and then director of research for the metals division, overseeing developments that extended far beyond magnesium extraction. He published papers on corrosion resistance and alloy development and extraction chemistry that became standard references in the field, contributing to knowledge that benefited industries across multiple sectors. He also mentored dozens of younger engineers, passing along not just technical knowledge, but also the lessons learned from working across cultural and national boundaries toward common goals. His story and the stories of the other German prisoners who had contributed to the Magnesium project remained largely unknown outside specialized industrial circles, mentioned briefly in company histories but not widely discussed or celebrated. The collaboration that had seemed so controversial and unprecedented during wartime became just another example of technical problem-solving once the immediate crisis had passed. Patterson had gone on to a distinguished career in chemical engineering, eventually joining the faculty at Stanford and supervising research into industrial extraction processes. He and Zimmermann remained friends until Zimmermann's death in 1992, corresponding regularly and occasionally collaborating on technical papers that drew on their shared experience. Hartley had retired in the early 60s but remained active as a consultant and advisor, working with companies developing new applications for seawater minerals and advocating for environmental protections that would ensure coastal industries could operate sustainably. The facility itself had become a national historic landmark in the 80s, recognized for its role in wartime production and its pioneering use of ocean resources, though the significance of the German contribution was only briefly noted in the designation material. Visitors to the site could tour parts of the operation and see displays explaining the chemistry and engineering of magnesium extraction, but few understood the desperate circumstances and unlikely partnerships that had made the facility possible. The ocean continued its eternal rhythms, waves carrying dissolved minerals just as they had for millions of years, indifferent to human efforts to extract value from that ancient chemistry. The facility drew water from those waves and returned it processed but essentially unchanged, part of cycles that transcended human timescales and human conflict. In the years after Zimmermann's death, his children donated his papers to the University of Texas, boxes of technical drawings and correspondence and photographs that documented his role in developing seawater magnesium extraction. Researchers eventually used those materials to piece together a more complete account of how the technology had emerged and who had contributed to its development, revealing the extent to which German prisoners had been essential to solving one of America's critical wartime industrial challenges.